So gear kinematics, you see, I hope that you can see this animation. So you see when this gear rotates in this direction and this gear rotates in this direction, they engage here at this point, and then they follow these two lines here. So I think they start from here, from this point. I'm trying to pick them up, and then they leave each other maybe at this point, hopefully. Yeah. So you see here that because of the involute curve or the involute profile, so they offer here constant speed ratio. And then this line here, this line between this point to this point here, this line is the line of action, where the action happens, where the two gears they start engaging. And these two arrows here shows you the forces between them. They push each other, they apply force on each other. And then this line here is the line of action, or the pressure line, because there is a pressure between the two tooth, so it's called the pressure line. So you see here this point, if you follow this point, it just goes down, right? The point, the dot in the middle, at the middle of these two arrows, it just goes down. If you look at the top gear, so at the top gear, it just goes from the root to the tab. And if you look at the bottom one, you look at the point, and then at the tooth, you will find that the point is going from top to the bottom, right? So coming here, why I'm saying that, because here you see that you have a driver, then you have a driven, and then you have this point, the point of contact. Okay, then at the start, when they start meshing together or engaging together, so the tip of the driven touches this point here on the driver, right? Then at the pitch point, where in the middle, exactly in the middle, with this line, if you remember this line, the pitch, the line of action, there is a point here in the middle called the pitch point. And then here it's at the end of the mesh when they leave each other. So we are going in this direction. They start here, and they start here in the middle, and here they leave each other. Okay, or the engagement stuff. So there is two motions here. One is called roll, and the other one is called sliding or friction. And you see here on this teeth, the sliding is going upwards, and on this teeth, the sliding is going downwards. And here is the same. So in this case, this sliding produces some friction. So that's why it's called friction. Okay. So there is like some research is going on this. They use polymer gears, and then they have checked how these gears fracture or fail. And then they found, for example, here, because of the concentration of stresses, etc. So there are some high stresses here, and then they start fracturing here. Also, they have found this due to the sliding motion. Okay, so on the driver, for example, it is under tension, so it is like this. So the face of the gear here is under tension, and the face of the gear here, or the profile, is under compression. And if you look at this picture here, you'll find that under the microscope, scanning electron microscope, something is called SEM, they found here that this is something similar. So you have here two similar to this, for example. So you have something, a depth here in between, which corresponds to this line, and then there is some compression here from this side, and then some compression here from this side as well. So this research is going on at the University of Birmingham, the School of Engineering. So there is one more important point. It's called interference. So in order to keep the velocity ratio constant, so we have to have conjugate action. And in order to have conjugate action, we have to have involute profiles, okay? So for correct tooth action, the points of contact on the two mating teeth must lie on the involute profile. So when these two teeth come together, they should meet on the profile. They should meet on the involute profile only. Okay? Why I'm saying that? If you remember, I said this is the base circle, and the involute part of the curve starts at the base circle, right? Starts from here to here. Okay? So this is the involute part. So the part from here to the dedendum circle, this is called non-involute portion of the tooth. So when the mating gear or the mating tooth touches the other tooth underneath this base circle, so this part on the right hand side is involute, but the part here on the left hand side is non-involute because it is underneath. So this portion here between here to here is non-involute. Okay, and this portion here is involute. So what we have here, we have involute part is like in contact with like non-involute part. This is denoted as interference. So they interfere with each other. So this is a problem. This is a problem in gears. We have to avoid this problem actually. Okay, it means one of the solutions is that they undercut this part. They undercut this part so that it doesn't touch when the step comes here, so it doesn't touch any material. But this makes the tooth weaker, and then here is the concentration of stresses, so it makes the stresses higher and prone to failure. One way of making sure that there is no interference is to try to keep the minimum number of teeth greater than 17. There are some theoretical background, there are some equations for this, but the number of teeth on the pinion should be greater than 17